Well, hello. Thank you all for coming this morning. My name is Paul Devine, and I'm here with Dr. Frederick Diaz from University College in Dublin. Thank you for coming, Frederick. We really appreciate it. So a little bit about Dr. Diaz. He is a researcher in applied fluid mechanics, and he's done a lot of hydrodynamic research, particularly focused on maritime structures, and been using ADCPs for how many years now, Dr. Diaz, Frederick?
5 years.
Yeah, and for those of you that haven't attended one of our Teledyne Marine events, Dr. Diaz presented at the last one in September or in October of 2019 in San Diego. Some pretty amazing measurements of extreme waves off the Irish coast. Dr. Diaz uses the data for both basic and applied research, right? And the applied research is related to renewable energy, resource characterization and structure design. But Frederick, I was kind of wondering, before we get started, how did you become, you are an expert in ocean wave measurement and analysis. How did all that start for you? How did you become interested in the ocean and extreme waves?
Well, that's an interesting question because of my background, I started in mathematics. And so I started with the so-called water wave equations, which are fascinating by themselves. So I was studying solutions to these equations, and then one day I started to realize that these might be purely mathematical solutions. What about the real world? So gradually I started to get interested in the waves in the ocean. First, I started with waves in the lab, but then that was not good enough for me. So I really wanted to understand the waves in the ocean. So and then in 1998, I was in New Caledonia when the Papua New Guinea tsunami hit. And so that was really the first time in my life that, I was seeing the damages of ocean waves, and I was there when it happened. So that's how it started.
Yeah, the way that you sample the waves with the ADCP, you never really stop. You don't sleep in between. You don't burst sample and sleep. You just go continuously. If there was a tsunami, you'd be able to catch it. You'd be able to capture it. The way
Yes.
that you use the ADCP is a little bit very unique. I also, in looking at your CV, I see you are a member of the Royal Irish Academy and the Norwegian Academy of Sciences. Can you tell us a little bit? I mean, how that has influenced your field research, or your analytical or your field research?
Yes, so one thing which is fascinating when you become a member of an academy is that there is actually a network of academicians, and there is one which is quite active in Europe. And so they have working groups between these academicians. And right now, I'm belonging to one of these groups, and the theme of is the changes in ocean circulation and the consequences for European coastal regions. So we are preparing a report. It should be available, I think, next year. And the target is key policies in the European Union. So that's really an exciting aspect of being part of an academy.
Yeah. So anything? Before you get started, anything else to add about how your research has changed over the last 2 to 3 years? How things have evolved.
Well, so the earlier, and this is what I will be talking about. We had a big project on rogue waves, and so obviously, I will talk more during the talk about these rogue waves. But we had a conclusion on what we think generates rogue waves in the ocean, and so the next step, which is the new project which just started, and I will mention it as well, is more on the impact of these extreme waves and the damage that they can produce. And so one key aspect is the wave breaking. So my new research now is really focusing on wave breaking, and I will say a few words about that as well at the end of the talk.
Yeah, that's a very difficult situation for an ADCP because the bubbles are our enemy, you know.
Yes.
Okay. Well, hey, thank you. We look forward to hearing what hearing what you have to say today. Thank you very much for coming, and we really appreciate your. We look forward to hearing your talk. Thank you.
So thank you very much for the kind introduction. And so it's well, a pleasure to be giving this presentation. And most of the results I'm going to show today, that was obviously done with some co-workers. So two postdocs of mine, Jason Flanagan and James Herrich, and also a collaboration with Francesco Fedele, Georgia Tech, and Professor Tayfun, who is now retired. So, well, a year ago, the situation, as you know, was quite different. So, and as I said earlier, it's always good that we see the waves. And so this was a field trip to the Aran Islands, and this is most of the wave group, the UCD wave group on this photo from a year ago. So that's a very important aspect of the research, to go to the field. And so when it comes to extreme ocean waves, well, it's a very complicated topic. We have few observations and there is no consensus. So it's really a hot topic. So here, just summarize on the slide, you can get some large waves simply with linear effects, and I will come back to it on the next slide. And so one example is the focusing of waves due to the continental shelf topography. That's the feature that surfers know well about. Also, the directional focusing of wave trains when waves come from different directions and they can pile up. Dispersive focusing, it's a bit similar. It's two waves in the same direction, but traveling with different speeds. And so one can catch up with the other one. And waves with opposite currents. So that's, for example, what happens in South Africa. And that in the with the Agulhas current, and then can generate some very big waves. So the current, in a sense, increases the wave height. And but also there are some nonlinear effects. I put two here. One is instabilities, and we know that there are instabilities inside ocean waves. And also there can be some enhancements of constructive interference by simply second-order bound nonlinearities. And the reason why I put two topics in red, it's because that will be the focus of the talk today. So, but one thing I want to emphasize is that nonlinearity is important to understand large waves. So under some conditions, which do not happen very often, waves locally propagate in an organized way or nearly in phase. That can lead to an unusual case of constructive interference, and that can lead to waves of large amplitude. But this in itself cannot explain the sizes of the observed rogue waves. And the discrepancies can be attributed to the fact that waves are nonlinear, at least, you know, these large waves. They are not sinusoidal, so typically they have shallower rounded troughs and higher, sharper crests. Such nonlinearities can cause an increase of 10 to 20% in crest height. So, as I said earlier, I really got interested into observing waves and wave measurements. And so here on this map, it's just to show the Irish Marine Weather Buoy Network, which is maintained by METOCEAN and the Marine Institute. It has been in operation since 2001. And so you see the wave buoys, M1, M2 in the Irish Sea, M3 to the south, M4 northwest, M5 in the south. I will also mention Kinsale. There is a gas platform there, and also I'm showing where the UCD wave group is, which is in Dublin. And interestingly enough, now we have a workshop, so with real instruments and with an engineer, and the workshop is based on the West Coast because this is where the action is. So that's the second star over there. So just to show one of these wave buoy, the M6, which is the one which is really far out, about 150 kilometers west of Ireland, where the yellow star is, and on this map you see the bathymetry quite well. And so this is what this wave buoy looks like. And so, of course, you know, it has measured some waves over the years. So even though, you know, there are not that many measurements, we have some examples of monster waves on the surface of Irish waters. So here are some examples. The first one here, a 23.4 wave in a sea state of almost 15 meters. So that's the significant wave height. That was measured in January 2014 at the M4 buoy. 26-meter wave at Killard on the 28th of January with a wave rider buoy. A 25-meter wave at the Kinsale energy gas platform in February of 2014. A 21-meter wave on February 2015 at the M3 buoy. And now the next one is our wave group Pride, the 20-meter wave measured at Killard in the same date, by the way, that this previous one on the 23rd of February 2015 with a Sentinel V ADCP. And more recently, during the Ophelia storm, a 26-meter wave at the Kinsale energy gas platform. Now here, one word of caution. You can imagine that often people ask me, you know, what is the highest wave that has been recorded worldwide? So we have numbers for this highest significant wave heights, and that's of the order of 20 meter. So this 20 meter, which is the record for the significant wave height, has to be compared to some of these 15 meters. So even though, and most of these 20 meters have been measured in the Southern Ocean. So in Ireland, we are relatively close to some of these huge sea states that has been recorded worldwide. And so then, you know, because of these 20-meter waves that we measured with the Sentinel V ADCP, then with Darrell, we had a short paper in the Marine Technology, finding monsters on the ocean surface. And that was a photo taken by TechWorks Marine, who did the first deployment. Well, I already mentioned the wave that we measured with the ADCP, but so in 2014, so you were asking earlier, Paul, so that's 6 years, the decision was made to measure continuously waves of the west coast of Ireland with the hope of capturing extremes. So we went for the Sentinel V, and the first set of measurements were in the winter of 2015. And that's when we had the February 2015 storm that we'll study in more detail later. Then we did it again the next winter, but unfortunately, the frame carrying the ADCP flipped over after 6 days due to the presence of very strong currents. So we don't have much data from that set. And then we did it again in the winter of 2017. And then we will refer to one of the storms we got, the Doris storm, during that deployment. And then we were supposed to deploy this winter, but then the deployment was delayed with COVID, but also the administration was very late to give us the permit. So now we have the permit, so we will deploy next winter instead. So the setup of the ADCP that we've been using, so the cell size about 1 meter, 1.2 meter, 30 there are two numbers each time because it was slightly different for the 2015 and the 2017. So 34 cells the first time, 38 the second one. The main difference was the ambiguity velocity. It was too small at the first deployment, and so we changed it to 5.5 meters per second in the second deployment. The blank interval 25 meter, so the first cell range 26 meter, and so continuous sampling for 3 months. So here's the ADCP on the left, and of course, you know, with extra batteries for the 3-month deployment. So the data was sampled at 2 Hertz, like standard wave measurements of oil platforms. We estimate the sampling error on the CREST and wave heights at 1 to 2%. We convert from instrument coordinates to geographical coordinates. We interpolate data to find the position of the maximum intensity to get the free surface, and we use the DWASP toolbox to estimate the directional spectrum. So again, you see the photo of the deployment of 2017, and then the 2 storms we are going to talk about is so the one in 2015 of the more to the south, and then the 2017 one of the Aran Islands. So, okay, here's the ADCP data from the first deployments in the winter of 2015. And so the first row is the both the significant wave height in green and the maximum wave height in red. And so we were very lucky. Just a couple of weeks after we deployed, we got this massive storm and these 21-meter waves. Then the second row shows the wave period, the Tmax, and also the TPs, the peak period. And then at the bottom, it's the water level. So we see the tides clearly. And so in some cases, we have 5-meter tide. That's the second deployment, the one of the Aran Islands. So again, about 3 months of deployment in winter, and again, the significant wave height and in green, and the Hmax in red, then the period, the TP, the direction of the waves, and then again the sea level. And so we are going to concentrate on this storm Doris. So it was not as energetic as the previous one. And also at the bottom, there is the spectrum time series. So these are the 3 months at the bottom. And then this is the Doris storm here with some activity that you see. Some comparisons between the various storms. So the 2 storms that we measured with the ADCP, Doris and the February 2015, and then the Killard one, that was a wave void, that was the year before, but it just gives a comparison. So the significant wave height, as I said, Doris was less energetic, but then the other 2 have 12-meter significant wave height, periods 10 second, 14, 17. Then this number is important to compute for rogue waves. I will just concentrate that the threshold for a rogue wave is sometimes taken as 1.25 for the crest height divided by the significant wave height. These are long waves, so typically 200-meter long. The Benjamin Fair index, I will skip this here. The skewness, so about the same for Doris and Killard. Much steeper waves for the February 2015 storm. The water depth is about the same for the 3 cases. Now, there is a number, the KD, which is the wave number multiplied by the water depth. So that's a key number in water wave theory because there is a threshold value of 1.363. And essentially, in 1D situations, then the nonlinear focusing stops if you go below that value. So what's interesting is that, there are values both above and below this threshold, but I will explain later that, what do you use for K in this expression? That's a bit difficult. Also, the excess kurtosis, as you see, it's very small, so that's an indication that there were not that many rogue waves here. So some subtleties of the transitional water depth. So defining, whether it's deep water, intermediate depth, shallow water, that's tricky with wind waves because of the wide range of wave numbers observed. So what we use here is the KP, the dominant wave number, to define this KD. So we focus our attention on the most energetic components with wave numbers at and near the spectral peak. Now, I don't want to go into the details, but wave directionality is measured by some coefficient R that you can compute. And the expression was given in deep water, and then the depth effects can change this R into a new R sub S, which is a function of R and also of this alpha S, which is the depth factor. So in directional seas, the modulation instability can also occur at depths below this critical threshold that I mentioned earlier, if this alpha S is positive. For waves propagating over a broad range of directions in the open sea, such instabilities are ineffective in triggering rogue waves as the excess kurtosis becomes negative, provided that RS is larger than 1. So a rogue wave regime is a more likely occurrence only if the surface spectrum is sufficiently narrow banded, so if RS is smaller than 1, as well as characterized by a relatively large positive excess kurtosis. In our case, both storms are in transitional water depths, prone to potential rogue occurrences since alpha S is positive, but the sea states are directionally spread and characterized with mostly negative excess kurtosis since this RS is larger than 1. So it's really, when you have to be careful when you make conclusions because it's subtle. But here we claim that, we are not in conditions where we have a lot of this modulation stability. The next, one of the problems as well is you definitely have non-stationary sea states. So then we came up with an optimal sea state duration to do all the statistics later. And you clearly see this minimum here. I won't go into the details, and that's why we decided to take 50 minutes for the optimal sea state duration. Now, again, showing this KD based on the KP, and you see the horizontal line here is this threshold, and DORIS is essentially above. The February 2015 storm is below. So, it's good to have these two cases above and below. Metocean parameters. So on the left, it's the significant wave height. By the way, we looked at the difference if we compute the significant wave height as 4 times sigma or simply as h 1/3. And there are some small differences, but at most of 5%. Then the mean zero crossing period here, I will skip this for now. And then the surface spectra at peak stage. So we get, the classical f to the -4 slope in both. But these sea states, they are broad-banded. The directionality, this is the showing it for DORIS. So it shows the directional spectrum on the left, and then the angular spreading function on the right. Another thing which is interesting to check is the if the waves are breaking. So there are some criteria, the Misch-Stokes limits. I'm running out of time, so I will go briefly, but essentially we are below these estimates. So, essentially there is not much breaking, but the thing is the onset of wave breaking can occur well below these limits. Okay, the dynamic excess kurtosis, as I mentioned earlier, it's essentially negative for both storms. So that's the dark curve here. Sorry, the dark curve is the HS, and then this is the excess kurtosis, but it's negative. So, and then the crest heights and wave heights. So let's forget about the wave heights, only the crest heights. So this is the threshold for rogue waves, and then this is the Rayleigh theory, linear waves, and then the Tayfun Fedele, and so on. So we have a good agreement. These are the experimental results, and this is the confidence bands here. We have a good comparison with these models. So this was for DORIS, same thing for the February 2015 good agreement with Tayfun Fedele, and all of these are quite close to each other. So the conclusions of the analysis of the non-stationary surface elevation series. So the Tayfun and Boccotti models describe well the characteristics of waves observed in relatively shallow waters. The largest nearshore waves observed with the ADCP don't exceed rogue thresholds. The modulational instabilities are ineffective in what we observe. And so it's really the second order bound nonlinearities that enhance the linear dispersive focusing and directional focusing of extreme waves. So this was published in a paper in Scientific Reports a few months ago with Fedele, Hertrich, Tayfun. So just in 2 minutes, I will talk about the High Wave project, which is a 5-year project that just started with 3 work packages, one on breaking onset and dissipation, one on breaking wave loads, and one on breaking wave erosion. And then, of course, with a lot of field measurements. So you see the ADCP here, so it will be one of the components, but there will be also traditional wave buoys and so on. So we will deploy an ADCP again. We'll do stereo video. We'll put even a seismometer inside a cliff, drifting and anchored buoys, a radar. The last anchor buoy was deployed, the first buoy was deployed last Sunday. We will also install weather stations because it's important to have the wind as well. And also we would like to collect real-time data, well, except for the ADCP for reasons that you know. So here, so if you want to know more about the project, I encourage you to look at the website, highwave-project.eu. And so this is in Nearshore. And so the first deployment of these ADCP is going to be here. That's facing the Atlantic, right? So it will be hit by big waves. So I thank TRDI for the continuous support. It's really great. And here's the list of, I'm not going to cite everybody, all the people who have been involved in this. Thank you.
Yeah, thank you very much, Frederick. You know, as you were presenting, you presented a number of parameters that could have been related to the occurrence of rogue waves. And the one parameter, this RS parameter, do you think that is that the most sensitive parameter, or is that the most predictive of whether or not we would have rogue wave conditions?
Yes, so yeah, it's definitely one of the important parameters, but at the end of the day, you know, it's well, the excess kurtosis, the excess dynamic kurtosis is, you know, a very important one, and here we show that, you know, it's very, very small or negative. So that's the main parameter that says that we, you know, we don't have the I mean, the modulation stability is not strong.
Yeah, I mean, if I'm a mariner and I'm trying to pilot a vessel, you know, I wave height makes sense to me. But you know, how do we as a vendor of instrumentation provide a summary parameter that is, you know, most indicative of, or that would predict whether or not you'd have a rogue wave condition? And should we add these? We don't calculate these parameters in our software. Right?
No, that's a good question. It's something that I know that Fedele has been working on this with the NOAA people to try to incorporate, some type of index inside WaveWatch 3 that would. I don't know what the latest is, because as I explained, it's complex. So, before we come up with a universal index, there's still some work to be done.
I see. Yeah. Okay. Okay. Well, we really appreciate your time. Thank you very much. And I hope you and everyone else in attendance stay safe, and keep washing your hands, and hope everyone's families are safe out there. Margot, do we have any questions from the group? We got any chat questions at all?
Nope, no questions.
All right. Well, thank you, Frederick, Dr. Diaz. I really appreciate it. Thank you very much, and hope you all have a good afternoon in Europe or morning here on the West Coast.
Thank you.
Okay. Talk with you. Good luck this summer, or good luck this next deployment, this next fall. Hope you pull together everything for the high wave. Good luck getting into the field.
Thank you.
All right. Bye-bye.